friends, in previous lecture we discussed the factor affecting the stability of conformation, that means the angle strain, torsional strain and dipole-dipole interaction. In today's lecture we will start the remaining part of stereochemistry of cyclohexane. Here the chair and board conformations are given. Chair and board conformations of cyclohexane. That means here if we see, this is a cyclohexane. Okay, this is the chair conformations of cyclohexane. That means chair form. This is first, and here this is a second form. That means here we give numbering here 1, 2, 3, 4, 5, 6. Okay, or we can give numbering here from this direction 1, 2, 3, 4, 5, 6. Now then here if we see this chair form, in this chair form the C2, C3, C5, that means C2, C2, C3, C5, C6 forms a one plane. Here again same this one, that means this 4 carbon, it forms the one plane. Okay, now the C1 and C4, here the C1, that means this carbon, this C1 and C4 they are above the plane. That means here if you see this C4 carbon here, the C4 carbon here above the plane, and here C1 carbon is below the plane in first conformation. Okay, that means these carbons are, C1 is below the plane in this conformation and C4 are above the plane. And in second conformation, here the C4 are below the plane and C1 is above the plane. Okay, it depends on the how to draw this cyclohexane. That means if we draw in this fashion, at that time the C1 is below the plane, and if we draw in this fashion, at that time C1 is above the plane. Okay, now this is about the chair form of the cyclohexane. Now what about the board form of the cyclohexane? The board form of the cyclohexane, that means here this is a simple board form. If you see this board form here, we draw this in this way. Okay, now this is third and here fourth. Now here numbering, that means 1, 2, 3, 4, 5, 6 carbon. Okay, here both forms. Now in both forms, if we see the C2, okay, C2, C3, C5, C6 forms one plane in both the third and fourth form. Third and fourth here in both form, they are in one plane. C2, C3, C5 and C6, they form one plane. Now if we see the in both conformation here, the C4, that means this one, C4 and C1 both are above the plane. Okay, the C1 and C4 both are above the plane in third conformation. Now in fourth, the C1 and C4 both are below the plane. So this is a difference between the third and the fourth. That means this is a interconversion of chair and the board forms. That means here, so friend, in chair conformation, this first one is the chair conformation and second one is the board conformation. In 1980, the Sachs, S.A.C.H.E. Sachs suggested that the cyclohexane could exist in two non-planar structure which will be free from the angle strain. First one is the chair form and second one is the board form. That means in 1980 the scientist Sachs, he suggested that the cyclohexane exists in a two non-planar structure. First one is the, and it is free from the angle strain. First one is the chair conformation and second one is the board form. Okay, and in chair form, the 4 carbon atoms are in one plane. That means I have mentioned here the C2, C3, C5, C6, they are in one plane, and this represent the average plane of the molecule. Whereas the 1 carbon atom, that means C4, one carbon atom, that is C4, is above the plane, and one carbon atom, that is C1, is below the plane, or vice versa. And in the board form, the 4 carbon atom, that means I mentioned here C2, C3, C5, C6 are again in one plane, while the C1 and C4, the C1 and C4, both C1 and C4 are above or the below the plane. Okay, this is a difference between the chair and the board form. Now the chair and board forms are interconvertible by rotation about the carbon-carbon single bonds. That means rotation about the carbon-carbon single bond. Here By simply we converting the rotation about the carbon-carbon single bond, we can convert chair to boat. Okay. Now, next, the axial equatorial hydrogen atoms in chair form of cyclohexane. So, friend, in cyclohexane, that means the cyclohexane, that is C6H12. There are 12 hydrogen. There are 12 hydrogen atoms in cyclohexane, and all of them, however, are not equivalent in chair conformation. That means here, if you see the figure 7.8 in chair conformation, here there are 6 hydrogen atoms in chair conformation. First, here A, having the 6 hydrogen atoms which are perpendicular to the average plane and parallel to the axis passing through the center is known as the axial hydrogen. That means here, I am repeating, in cyclohexane there are 12 hydrogen. Out of these 12 hydrogen, the 6 hydrogen atoms which are perpendicular to the average plane and parallel to the axis passing through the center are known as the axial hydrogen. That means here, first, this is the axial bond. Here 1, 2, 3, 4, 5 and 6. Here 6 hydrogen, and they are called as the axial hydrogen or the axial bonds. Okay. Now, in chair form, there are 6 other hydrogen atoms which are projecting outward and are in the average plane of the ring are known as the equatorial hydrogen. That means this one here, equatorial hydrogen. That means having the 6 equatorial hydrogen. That means this 1, 2, 3, 4, 5, 6. They are represented as in this way, equatorial bonds. They are the equatorial bond. They are here axial. This is, they are perpendicular, this axial bond, and these are the equatorial bond. Okay, that means in cyclohexane there are 12 hydrogen atom. Out of these 12 hydrogen atom, 6 hydrogen atoms are axial, while the 6 hydrogen atoms are equatorial. Okay. Now, the equatorial bonds are also project above and below the plane of the alternatively. That means here, if we see, this is above, this is below. That means the equatorial hydrogen, it sometimes it is projected above and below the plane alternatively. And in the chair conformation, each carbon atom has one equatorial bond and one axial bond. It means if we draw the structure of cyclohexane, and in structure of cyclohexane here, one bond, that means in chair conformations of cyclohexane, when we draw the chair conformation, the each carbon atom has one equatorial. That means this, if we see this carbon atom, each carbon atom has one equatorial. That means one equatorial and one axial bond. That means if you see this carbon, here again one axial, one equatorial. If you see this carbon, here one axial, one equatorial. That means in chair conformation of cyclohexane, each carbon atom has one axial and one equatorial bonds. And it should be noted that, that means if the axial bond at any carbon in projecting above, and then equatorial bond at the carbon, it should be projecting below the plane or vice versa. That means if we draw this here, this carbon, here the hydrogen is above, that means this is axial, so remaining hydrogen is definitely equatorial. That means one axial, the another it should be the equatorial. Okay, that means one should be projecting above, the another it should be below. That means when we draw this here from this carbon, if we draw this hydrogen above, definitely the another hydrogen it should be the below. Okay, this is a criteria, or we can draw a vice versa. And the equatorial bond at any carbon atom is parallel to the next or the previous, that means carbon-carbon single bond of the ring. For example, the equatorial bond at C2 is parallel to the C3 and C4, while the C1 and C6 bond is projecting above. Okay, this is a simple about the cyclohexane. That means cyclohexane in chair conformation. Okay, it having the 12 hydrogen atom, the 6 hydrogen atoms are axial, while the 6 hydrogen atoms are equatorial. And when we draw the chair conformation, when we draw the chair conformations of this cyclohexane, at that time each carbon atom having the one bond is axial and other is equatorial. Or if we draw projecting one hydrogen above, the another should be below. Okay. Now then next point is the ring flipping. This is the most important in chair conformations. Ring flipping, when one form of the chair is converted into another chair, is known as the ring flipping. Ring flipping, that means conversion of one chair to the another chair. Okay, this is called as the ring flipping. And after ring flipping, this is the most important. After ring flipping, the axial hydrogen atoms becomes equatorial. I am repeating, the axial hydrogen atoms becomes equatorial hydrogen atoms, and equatorial hydrogen atoms become axial. This is the most important. That means after when you perform the ring flipping, in a ring flipping, the axial hydrogen atoms, it will be converted into equatorial, or equatorial hydrogen atoms, it will be converted into axial. Here this is axial, this is equatorial. Here axial, this is H0 here, H0 here, equatorial. I have mentioned here H0, that means here equatorial, and here H dash, that means the axial. And if you performing the ring flipping by in this way, here the directions are given here. This bond will be stretched in this way and this way. Okay. Now then it is the ring flipping, and after ring flipping, suppose if we focus on here at 2 number carbon, or here 1 number carbon, suppose here 1 number carbon, here the H dash is axial and here H0 is equatorial, and after ring flipping, here the H0 is axial while the H dash is equatorial. That means in first conformation the H0 is equatorial, and in second H0 is axial, while in H0 H dash in first conformation it is axial, and after ring flipping it become equatorial. The H dash become equatorial. That means this is the interconversion of axial and the equatorial. Now the next, the comparison of chair and boat conformation. That means if we compare the chair and the boat form, so this is a chair form and this is a boat form. Okay. In both, that means in chair and the boat conformation of cyclohexane have a no angle strain, as all the carbon atoms are all the atoms are at the 109.5 degree. Okay, that means in this both, that means in chair and in boat form, it having the no angle strain. Okay, now in chair conformation, the hydrogen atoms attached to any two adjacent carbon atoms. Atoms are the staggered, and hence the torsional strain is minimum, and the strain is free chair conformation, and can be verified by drawing the Newman projection formula. And this is called as, this is Newman projection actually. This is a Newman projection form of the chair, and this is a Newman projection form of the boat form. So how will you draw this one? Here first this is a front side carbon. Okay, now then first draw this y form. That means we know the alphabetical letter Y, that means this is Y form. Okay, now then this is a front carbon, and here the circle, it becomes the back carbon. Okay, and here again adjacent to this, again draw here circle, and here again this Y. Okay, this is front side, and the circle, that means here back side carbon. That means here the back side carbon, that means here 1 number, then 2 number, then 3, 4, then again backside carbon 5, and here 6, and here we are joining this one, and remaining are here hydrogen. Now then here numberings are given, that means here 1, 2, 3, 4, 5, 6. Now then if we see here C2 and C4, the front carbon, that means here this is most important. Here I mentioned here the C2 and here C4, they are the front carbon, while the C5, that means here this back side, here the C5 and here C1, they are the rear carbon, that means they are the back side carbon. Okay, now in boat form, this is a boat form. Okay, boat form, here numbering starting from here 1, 2, 3, 4, 5, 6, and here HF, that means here the flagpole hydrogen. Again we draw the Newman projection of this boat form. Here again first draw a circle, now then this is Y. Okay, Y form, again this circle and this Y form. Now then joining this number here, now this is 1 number. Okay, here 1 number, 2, 3 is the back side 3, 4, again 5 back side, 5 6. Okay, and here this is a flagpole hydrogen. Okay, now here in both form, the C2 C6, the C2, that means here the C2 and C6, they are the front carbon, while the C5 and C3, here the C5 and C3 are the rear carbon, that means they are the backside carbons. So in this way we draw the chair conformations and the boat conformations. Here this is chair and this is boat conformation and their Newman projection form. This is the most important, chair conformations, and this is the Newman projection of chair. This is boat, and this is a Newman projection of the boat form. So this is a simple explanation about the a Newman projection of chair and the boat forms. Now then next and here from this chair and the boat, okay, here we draw this chair conformation and its Newman projection, and here boat conformation and here Newman projection. Now the torsional interaction of the 4 pairs of eclipsing hydrogen and the flagpole interaction, they increases the potential energy of the molecule in boat conformation, because in a boat conformation there is flagpole hydrogen interaction. Due to the presence of the flagpole hydrogen interaction, the increases the potential energy of the boat conformation, and the energy of the boat conformation is about 7.1 kilocalorie per mole. That means in boat conformation having the energy is 7.1 kilocalorie per mole, and it is higher than the chair conformation. Okay, it's higher than the chair conformation. That means in chair conformation it possesses the flagpole hydrogen interaction, and the flagpole hydrogen interaction having the energy is about 1.7 kilocalorie per mole. That means this is a higher than the chair conformation. That's why we conclude that in chair conformation, the chair conformation is more stable than the boat conformation. If we discuss the stability of the, which is more stable, that means chair is more stable or the boat is more stable, and the answer of that question is simple: the chair conformation is more stable than the boat conformation. Why? Because in boat conformation there is presence of flagpole hydrogen interaction, and due to this flagpole hydrogen interaction is about a 7 kilocalorie per mole, having energy 7 kilocalorie per mole, and such a interaction or such a flagpole hydrogen interaction is absent in chair conformation. That's why the chair conformation is more stable than the boat conformation. Okay, now then the skew and the boat form, that means the skew boat or the twist boat. In case of the skew boat or the twist boat, that means the skew boat, it is also called as the twist boat. Okay, now here the structure, that means this is a boat form or this is a twist boat. Now then how will you convert the boat form to twist boat? It's very simple. Here this is the a boat form, and here we know the in the boat form here the flagpole hydrogen. Now then this is a move apart and here move together. That means this one, that means this HA and this H1, that means this carbon, they are the move together and this move apart, and we get the twist boat. That means this way we convert boat form to the twist boat. Now a modified boat conformation has been suggested in which the flagpole hydrogen are away from or move away, and therefore the van der Waals strain or the steric strain is decreases. That means here in boat form this flagpole hydrogen they are come close, while in case of the twist boat this flagpole hydrogen they are the away from each other, therefore they are the van der Waals strain or the steric strain is decreases, because here these flagpole hydrogens they are away from each other. Similarly, the torsional interaction due to eclipsing hydrogen are also decreases to some extent, and such a boat is known as the skew boat or the twist boat. That means this is called as the skew boat or the twist boat. In a torsional strain, I am repeating, the torsional interaction due to eclipsing hydrogen are also decreases in some extent, and such a boat is known as the skew boat or the twist boat. That means here in a twist boat such a interaction, or the skew boat such a interaction is absent. Why? Because these two flagpole hydrogen they are the away from each other. Now that means we conclude that means in the twist boat conformations has the energy about 5.5 kilocalorie per mole. In twist boat, having the energy is about 5.5 kilocalorie per mole. That means which is less than that of the boat conformation. Therefore, we conclude that in twist boat, that means the twist boat is more stable than the chair conformation. We conclude that the twist boat is more stable than the chair conformations. That means this is a simple conclusion. Okay. Now then the half chair conformation. We will draw the half chair conformation. This is the chair. Okay. This is the chair form, and here we draw in this way chair form and give numbering here 1, 2, 3, 4, 5, 6. Okay. Chair form. Now then this carbon is stretched in this way. Okay, from your upsides, and here we get the half chair conformation, and here in half chair conformation give numbering here 1, 2, 3, 4, 5, 6. Okay, now in half chair conformation the carbon atom, that means C2, C3, C4, C5, C6 are in one plane. That means this C2, okay, C2, C3, C4, C5, C6, they are in one plane, while the C1 carbon atoms, it is above the plane. Okay, it is above the plane. And when the bottom carbon of chair conformation is lifted upwards, that means this carbon is lifted upward, so that the 5 carbons are in the same plane. That means these 5 carbons are in the same plane, and only one carbon atom is above the plane. Such a conformation is called as the half chair conformation. Such a conformation is called as the half chair conformation, and it has the angle strain as well as the torsional strain lies about 11 kilocalorie. That means the in half chair having the angle strain as well as the torsional strain is about the 11 kilocalorie per mole above the chair conformations. Okay, and it is the least stable conformations of the cyclohexane. It is the least stable conformations of the cyclohexane. Now the next, the potential energy relationship among the conformation. That means as one start converting the chair into boat conformation, the following energy changes take place. That means overall the relationships are summarized here. That means here the charts is shown below. Potential energy, when we convert the chair to half chair to twist chair, or the chair to boat, friend, we know that the thermal energy is associated with the molecules. Thermal energy, it is associated with the molecules at room temperature, is the order of 15 to 20 kilocalorie per mole, and the energy required for the conversion of chair into boat conformation is only about 11 kilocalorie. That means we convert chair to boat. The conversion of chair to boat conformation is only about 11 kilocalorie per mole. Therefore, the chair conformation is constantly converted into the boat and vice versa, just as the staggered and the eclipse conformations. Okay. Now, the conformation of open chain alkane cannot be separated from each other. Similarly, it is also not possible to separate the chair form of the boat form. It is also not possible to separate the chair from the boat form. Okay. Now the chair and the boat conformations are therefore always in equilibrium. However, the population of the chair form is very high as compared to the boat form. At 25 degrees Celsius, only one out of 1000 molecules will be in the boat form. Okay, and here the stabilities are given below. That means first here chair, then half chair, then twist boat, then boat, and here twist boat. Okay, and here the energy is associated with the molecules. Okay, here it is a simple the stabilities of, that means potential energy relationship among with the conformations of the cyclohexane. So friend, never miss a video. Subscribe to my YouTube channel. Okay, thank you.